Anand, you're back in robotics. What's the current state of the market?
Hi, thanks for having me. Yeah, it's exciting to be working on this and rethinking robotics problems again. I think the current state of the market is interesting and exciting. I think robotics has been in this sort of fragmented state for more than a decade now, where there's been many different sort of point solutions been developed, whether it's for autonomy, whether it's for AMRs inside factories, all sorts of different types of applications, but in a very fragmented way. I think with the advent of new sensor technologies, new ways of thinking about robotic intelligence, new AI models, I believe we are at the cusp of something interesting where I believe for the first time you will see the ability to build horizontal intelligence that can go across different robotics applications. And I don't think we're there yet, but I think we are on the cusp of that happening, which I think will be really exciting for robotics. At the risk of using a cliche, like the chat GPT moment for physical robots. And I think that the ability to build horizontal intelligence that works across different robot form factors, across different robot applications, I think, and being able to do that with really low cost, inexpensive hardware, I think will really unleash the use of robots in a variety of different domains for the first time in a way I think that we have all been imagining and hoping will happen as roboticists for a couple of decades, but I think it's finally going to happen probably in the next 10 years. So that's what I think is happening in robotics.
Interesting and exciting. I like that. You're right. The excitement is around robotics, and it's not limited to one robotics application. It's limited to, it's basically unlimited. Let's get rid of the word limited. It's an unlimited opportunity now. Are we entering the golden era of robotics that could potentially usher in some Jetsons creations?
I think, as I said, I think we're on the cusp of it. I don't think we're there yet because there are some key tools in the toolbox that are in development now in a variety of different companies, including at my current company at Vayu, which I think are necessary to unlock this incredible potential of robotics. But as those tools become mature and get deployed in a variety of different real world applications, I do think you will see a Jetson-like age. I think you see a lot of companies building all sorts of form factors, including humanoids. And I think that's still just the tip of the iceberg, if you will. I think there's so many different possibilities that we haven't even thought about because the macroeconomic challenges are well known, right? I mean, labor shortages continue to be a challenge. The fact that we are seeing sort of insourcing and near sourcing from a manufacturing perspective, and that will continue to be a trend. The fact that you're seeing e-commerce explode and there's so many needs for people to get goods delivered in a variety of different situations. All of these different sort of macroeconomic trends continue to drive economic need for automation and in many different sectors. But the technology hasn't caught up until I think now it's starting to. So yeah, I think the next 10 years from a product development, technology development, and deployment perspective, as you called it, could really be the golden age for robotics.
Is this where value comes in because you're taking a high quality, low cost approach where the economics make sense when if you're putting it in a warehouse, you're putting it in a meat packing plant, or you're putting it on the road, the economics are starting to make sense. Is that why you co-founded Vayu now?
Yeah, I mean, I think Vayu actually, yeah, the sort of Vayu was co-founded really based on, conversations I used to have with my customers as the CEO of Velodyne, which was my previous company, because often the conversations would be around scale, right? I mean, we had, all these, really smart customers who had built incredibly sophisticated autonomous vehicle platforms. And in order to do that, they had thrown like 50 sensors and a ton of compute and all of these things at the problem. And back in 2020, 2021 timeframe, these systems started working fairly well. And then people started thinking about scale. So often the customers would come to me and say, hey, these things are working. We have 150, 200 systems on the road. Now we are starting to think about how to build 100,000 systems. And by the way, cost needs to come down by a factor of 20. How do I do that? And I would basically shrug my shoulders and say, I have no idea how you do that, right? Because I don't know how you increment your way into a factor of 10, factor of 20 improvement in scale in anything. And this was really the sort of genesis for the foundation of Vayu, was this idea that, yeah, there was going to be this drive for scale, but there were some new tools in the toolbox that needed to be developed, and we would have to rethink to some extent robotic architectures.
Was the current approach and the approach that you were mentioning, which is still being used by not some companies, not all companies, too sensor heavy. There was a report on CNBC this week that the Waymo vehicle, this is unverified, but it was a CNBC report, so I'll cite CNBC on that the Waymo vehicle costs, the Jaguar costs $300,000 per vehicle. Without Alphabet's capital, that's not scalable. And then on the other hand, for a fraction of that, at $30,000, you have a Tesla Model 3 that in theory, I'm not saying it works, but in theory, could achieve full autonomy. You're taking an approach of value where you're saying high quality, low cost. Do we meet somewhere in the middle? So let's call it, I don't know, Acme Fleet says, okay, and I need a fleet of 100,000 of these. We're going to take this approach because the economics. Does that become this overarching driver where the market is not going to go for the super high end, where you have Alphabet subsidizing you, Amazon subsidizing you, and the market say, okay, you have to make a business here?
Let's actually start with the economic piece, and then we'll talk a little bit about the technology philosophies, which really, you talked about the two sort of ends of the spectrum, right? The Waymo philosophy and the Tesla philosophy. So first, from an economics perspective, I think cost of hardware has to come down, right? Like most business models cannot bear a $300,000 cost of bill of materials of a vehicle, let alone cost of ownership, which will be much higher because of other things like software costs, human in the loop, insurance, maintenance, et cetera, et cetera. And so, because like even to move people, I mean, the cost of a driver is, is $100,000, but your Uber driver makes roughly $1 a mile. So it's not, you're competing with that, right? And so it's really not easy. But if you're moving goods within a factory, if you're moving goods even outside, the costs that you can bear are even lower economically, right? So forget about $300,000. I mean, we believe for goods movement vehicles, you have to be basically in few $1,000s, right? So like there are companies, who have built self-driving cars for delivering pizzas and goods. It never works, right? Because like how many $10 pizzas do you need to deliver before you can amortize the cost of a $200,000 vehicle? And so economically, there is no doubt that you have to bring the cost of hardware down. So that's one point. Now to the second point that you made, which I think is really where the industry has gone back and forth, right? There's this one school of thought, which is, hey, like these are safety critical systems. You need the right levels of guardrails to make these systems safe. And this is why we need a lot of sensors. There's so many corner cases, et cetera, right? This was the reason of existence for LiDAR and so on. And then there's the other school of thought, which is, hey, neural networks have gotten so smart and intelligent that they can actually do a lot of things with just cameras. And that's going to be sufficient to solve self-driving. And both, to some extent, we believe both are correct, right? But the reality is you need that neural networks have become capable enough to solve most cases when it comes to moving through the world and driving and doing that with passive sensing. However, there are always going to be situations where they do something completely weird and you will not know why they do that, right? And so you need guardrails for the system, so this combination of having neural networks solve a large fraction of the problem with the right sort of guardrails, which is maybe the right set of sensors, not very expensive sensors, but necessarily sensors with the ability to see the world fairly robustly, I think is going to be the right answer, right? Which is, and how do you come up with that right combination of deep learning based software, but adequate sensors and adequate guardrails on the hardware side? That was really what we set out to do at Vayu, right? And so I do think that there is an answer in the middle which will ultimately succeed.
There is an answer in the middle. I've talked to some engineers that they're saying that Waymo is working on a licensing version. This was confirmed in a Fortune interview. But then speaking with the engineers, they're saying that Waymo's having a very hard time. They use the term making a light version of their stack. And so that gets, if you start with, let's call it the fancy stack. We'll use the term the fancy stack. And then you try and get it down to this makes economic sense stack. There seems to be a big divide from engineering and how you're going to achieve that. I was reading today, there was a case in the California Supreme Court about Uber and what they're doing with the drivers, the idling time. They have to pay them $25 minimum an hour. So Uber is turning it off and not allowing them to idle. And then same thing is happening in New York. And Uber drivers' wages are actually plummeting, in some cases down 50, 60, 70%. Will the labor bills that are all these minimum wages on drivers, could that potentially accelerate the adoption of autonomy, especially from a delivery standpoint? You're working on the Vayu 1. Neuro has their NeuroBot. Could this accelerate this just based on the economics? Because you can't afford to pay somebody $25 to deliver you a $15 pizza. It's not going to happen. If we look at data around Uber Eats, where there is minimum wage, consumers are not opting for the Uber Eats anymore. They say, well, I'll get in the car and I'll drive. I'm not going to pay the delivery fee. And it just seems that from an economic standpoint, it's going to impact the restaurants. They're going to have to raise prices. And it's going to be this downward cycle. Does autonomy come in here as the white knight and really truly save the day?
I think the answer is yes. The right kind of systems can, right? Like if you can build a system that actually is, like we have been talking about, at a low enough hardware cost. So you use Neuro as an example. I mean, our system basically is capable of doing similar functionality, but basically, it costs, probably 20x less than what I know roughly the Neuro system might cost. And that's what you need to do, right? So you need a low cost enough system with low cost enough cost of ownership and operation with the right level of autonomy. If you have that, then I think these systems actually do end up being the right way to get goods to people. This is not to say that this is the sort of one answer to all goods delivery, but I think it becomes a huge part of the solution. As you said, like when you look at Uber and DoorDash and these kind of companies, even with the amount of markups they charge on their average order is like 40% marked up and so on, they're still like barely making ends meet from an economics per order perspective. And at the same time, the amount that the drivers are making is plummeting. So clearly the economic model doesn't work for society. And couple this with the fact that e-commerce is just increasing, right? And consumers' behaviors are trending towards ordering more and more stuff online. So something's got to give. And I do think that robotics is a large part of that solution. In some cases, there will be models where they will augment humans, right? Where you could have a hub and spokes model where maybe there's some humans moving goods in some in some legs of that journey, and robots take over at some other legs of the journey, or vice versa. So I think those kinds of models will emerge eventually to help solve for demand, while at the same time making sort of the humans in the loop much more productive and efficient. But I completely agree with your broader point, which is that the economics dictate that something's got to give, right? This doesn't make sense anymore. All of these companies in the middle who are massively marking up goods just to be able to deliver them to you just doesn't make economic sense. And when you couple that with the fact that cost of labor is going to continue to go up, it feels like there has to be a better solution for society.
The consumer is going to cry uncle at some point. Grocery store prices are up 20%. Eggs, I believe, are higher than that. Orange juice is up. Consumers saying, you know what? We're done. And if you look at robotics, you add robotics in the mix. Robotics can beat inflation. They can lower the cost of goods. I don't know why we don't hear talk out of the Federal Reserve for that. Because if you look at the Vayu approach, they put your system into, let's call it a global supply chain or a global food processing chain. Based on your economics, you can easily lower the price by 20%. That could be passed on to the consumer and beat inflation, which then has a positive benefit for not just the U.S. economy, but the global economy. How would you explain to the audience what the Vayu approach is to robotics and autonomy?
The Vayu approach to robotics and autonomy can be best described as follows. I think we have come up with an approach that combines low-cost hardware that really enables robotic systems to be built for thousands of dollars versus tens or hundreds of thousands of dollars. This is on the backs of our own sort of sensing approach, which is very high quality, but still much lower cost than traditional LiDAR, as well as the ability to run the autonomy systems on low cost compute like ARM processors versus very expensive servers. So we have built systems that are very low cost hardware, but at the same time, with a level of autonomy that allows these systems to operate across different operational domains, whether it's inside a grocery store, inside a restaurant, or on a city street, delivering goods to people. And so the combination of robust software and low-cost hardware allows us to really bring down the cost of moving goods to sub 50 cents or even sub 25 cents. And I think when you get to those sorts of economics, you can really democratize this problem of getting goods from point A to point B. And I think that is a net positive for small businesses. It's a net positive for consumers. It's a net positive for large businesses and large supply chains. And so that's really what we are trying to do, is to really change how goods go from point A to point B to a point where you don't have to think about that cost at all. And that becomes like almost a net transparent cost to the end consumer and to small businesses.
It's a game changer. ARM is low cost, but it's also low power. What efficiencies are you unlocking by using a low power chip versus a GPU cluster that's going to take a lot of power to run?
That's a great question, right? Because ultimately, power is really important for anything that moves and runs on batteries. And the thing with when you have to build things with low power processors and so on, it turns out you can really build these robotic systems that effectively can move around the world and move goods through an entire workday without having to recharge or even swap a battery, right? So our systems basically can run for, in the range of 6 to 8 hours on a single 2.5 kilowatt hour battery, which is incredibly energy efficient. And of course, which means that the carbon footprint for a system like this is a fraction of what it would be for your average DoorDash or Uber driver to move stuff. And that's the power. That's it's really connecting the sort of technology unlock that is made possible with ARM processors and low power processors to actually, carbon efficiency of moving goods. And there's like a direct actual line that you can draw between the two. And that's why I think it's really the way of the future. And this is how I believe goods should move, because the carbon footprint of moving your groceries, let's say an average of 35 pounds of groceries from the grocery store to your home, if you are even using Instacart or you're going to the grocery store yourself, is probably a few hundred grams of carbon. And that can come down to basically in the range of 20, 30 grams of carbon with, a 2.5 kilowatt hour battery, sort of the type of vehicle that we have built at Vayu.
Why is there not a larger emphasis put on energy efficiency when it comes to developing autonomy? You don't hear it very often. In certain engineering circles you hear it, but from a mainstream perspective, I read more investment reports than I care to reveal publicly, but I read a lot. And the theme is invest in energy, invest in data centers. It's going to need energy. It's going to need power. Invest in utilities. I don't remember when investing in utilities was ever sexy. Now it seems it's one of the sexiest trends out there is go long utilities. But for this technology to work, as you clearly articulated, is going to take energy efficiency. But yet it's never discussed. Why is that?
I think it's just what part of the hype cycle the technology is on, quite frankly, right? I mean, I think it's just that we have still been on the sort of first wave of the hype cycle where it's just been about getting things to work. I do think that when people start thinking about scale, and there are people who are starting to think about this more, energy efficiency, cost efficiency, all of these things will become much more important, and actually the things that will ultimately distinguish a winning solution from sort of solution that also ran. So I think it's just timing more than anything else. I do think that as these systems work, people are still struggling to prove out business models in certain cases. But as you see some of these second generation systems starting to come online, you will see a lot more focus on efficiency, energy efficiency. I think, we are not focused on this, but like an orthogonal area where I think this will become also pretty interesting is trucking, as an example, right? Where, people are starting to people were building autonomous trucks before. Now you're seeing the second wave of autonomous trucking companies come to fruition. But I think they will be much more energy efficient if they do things the right way. And I think that has huge benefits for trucking, obviously, because you basically make your money back on the system in just fuel savings on an autonomous truck.
When do you see more energy efficient sensors being developed? Because there are multiple, you're going to have a, let's call it sensor heavy approach, you're going to have a sensor light approach, and you're going to have the Vayu approach. Will some of those sensor heavy approaches start to innovate and get energy efficient as they start to ramp up the economics of the business? It's
an awesome question. I think we spent a lot of time thinking about sensors when we started Vayu. Obviously, I had spent about 6-7 years working on LiDARs. My co-founder Mahesh came out of Apple, and he has also spent a lot of time in his career building LiDARs and designing LiDARs. And we spent a lot of time thinking about efficiency versus quality, right? Energy efficiency versus quality. And we came to the conclusion that, if you can get away with using passive sensing, which is what we do with Vayu Sense, and we can talk about that in more detail, that's the best way to keep energy efficiency, because ultimately the problem with active sensors, especially with laser-based sensors, is that the wall plug efficiency of lasers is just horrible, right? It's just been the case forever, and that's just physics, right? Unless somebody comes up with a completely new way of lasing, you're never going to like push past the wall plug efficiency of lasers, and that ultimately becomes the biggest energy hog. Not to mention the fact that a lot of the laser systems also need active temperature control, and they end up using a thermoelectric control unit, and that's got horrible wall plug efficiency too. And so then you have this sort of cascade effect of really poor energy choices. So we came to the conclusion at Vayu that if you can extract as much information as you need without actively illuminating the scene using passive sensing, that's your best bet. And so that's the approach that we focused on, is to actually see if there's other ways to extract information about the three-dimensional world without actively illuminating the scene. And if you can do that, that's the way to build the most energy efficient sensor.
Passive sensing. Now you've triggered the curiosity in my brain. What is passive sensing?
So when you think about what you're trying to do with sensing for robotics and autonomy, obviously you're trying to extract as much information as possible about the three-dimensional world around the robot. The most common way of doing this, of course, is to just use a standard camera, which is a CMOS imager. And all it's doing is it's just absorbing ambient photons or ambient light, right? So the light has traveled from the sun or from some illumination source in the environment. It's hit the target, and then it's come back, and then it's hit your CMOS imager, and you're measuring the average intensity of the photon. So this is fundamentally like what you're doing with a passive sensor. Now, it turns out that the camera has lots of known failure modes. It doesn't get all the information that you need. And so then people realize, oh, this is not going to work. So I have all these situations where I need to do something. I need to get more information, low light, high dynamic range, all of these situations. So I'm going to start actively illuminating the scene, whether it's using radars in a certain part of the electromagnetic spectrum or LiDARs, which is another part of the electromagnetic spectrum. And you're basically throwing out electromagnetic waves. Now you're getting them actively back, collecting them, and then you're trying to infer what's happening in the scene, right? And as we just discussed, that active illumination process, it becomes very energy inefficient. And so then we started thinking about the problem and said, hey, let's actually look at biology, right? And let's look at biological systems. Biological systems, turns out, do pretty well with just passive sensing. But I mean, and this is famous sort of Elon statement about like, oh, we don't have laser beams in our eyes. Half correct, right? But if you think about biological systems, they actually do more than just look at average intensity. They look at other properties of the light in the passive light field. Like there's animals that use polarization cues, for example. There's animals that use multiple apertures, compound eye sort of structures like that flies use or bees use. And so it turns out that biology has solved the problem, but it solved the problem by not just extracting average intensity as we traditionally do in a camera, but extracting other properties of light. And so that's what we started looking at. So when I talk about passive sensing, what we do in Vayu is we extract other properties of the photon other than just average intensity. We measure the polarization states of the photon. We measure angle of incidence of the photon. There's many other properties that the photon has in the passive light field. And then and fuse all of that information together to really derive a much more robust understanding of the world. And it turns out that you can actually overcome a lot of the inadequacies of a traditional camera if you do that, and you can do away with the need for active illumination. So that's the approach.
That's got defense applications written all over it. Is that why Lockheed Martin Ventures invested in your seed round along with Khosla?
Definitely, right? I mean, I think this does have applications in defense as well. Obviously, while I cannot talk about the specific applications that Lockheed or any of the other customers might be interested in, the general comment, as you know very well, is true, which is that in any defense application, active illumination is just a nightmare to deal with, right? I've had, customers say like, hey, your LiDAR basically lights up like a Christmas tree, and my enemy combatants can see it coming like, a mile away, right? And so it becomes an impossible situation to deal with. And so anything that you can do without active illumination is a massive advantage for defense.
You don't want to sit there Hi, here I come, bad guy.
That's right. Here's my autonomous system with 60 LiDAR or like whatever, 50, laser beams shooting out of my vehicle. And oh, I know exactly where this thing is. And all I need often with, near IR sort of LiDAR systems, you can basically see them with basically night vision goggles. And it becomes very hard to function in a lot of environments. And so yeah, definitely a lot of interesting applications if you can do a lot more without actively eliminating the scene.
Is passive sensing the B-52 of ground autonomy potentially?
It's very powerful if you can get it to work. And the challenging thing is no free lunch, right? So here's the challenge. The challenge is that depending upon the situation, depending upon the light conditions, different properties of the passive light field or the photon are important, right? And so the question is, how do you know what to look at when? This is where modern neural networks come in, where you can actually combine all of these different parameters of the photon and then train neural networks to figure out what to pay attention to at what point in time. And so it's more complicated than I make it sound, but that's what you need to do. But if you do that well, then yes, and I think it can be very, very powerful. It can really make autonomous systems very viable in these sorts of environments, very hard to detect.
Outside of defense, what other applications do you see for passive sensing? Is it going to be inside of the warehouse? Is it going to be on the loading bay, in the yard, on trains perhaps? I know there's a lot of investments being made in trains by the class ones to figure that out. Where do you see this potentially being deployed?
Basically, the number of applications is really large. And I think if you take a step back and think about it, any situation you want to measure depth and in terms of, by the way, that not only do you get very robust depth, but you can also do things like detect material properties, detect shapes of objects and things like that. So almost any application where you're trying to either sense depth or sense other properties of the environment, you could use passive sensing. So what we are finding is today, if you look at the robotics world, you have LiDAR, which is this expensive solution or expensive option, often too expensive for a lot of robots, right? Like in a lot of applications, LiDAR becomes too expensive. Or you have stereo cameras, which are obviously very cheap, but with all of these known failure modes. And we believe what we have developed fits right in between those two and can actually give you fairly good, robust, high performance, but with the cost basis of a standard stereo camera without breaking the bank like a LiDAR does. And so anywhere those sorts of sensing modalities are used, we could find applications for this technology.
Where do AI foundational models come into the picture to enable us?
It's a great question, especially such a topical thing, right? Everyone's talking about AI foundation models these days. And I think to some extent, it's important to separate the hype from the reality of it, right? I think if you think about robotics from first principles, there's two things that robots need to do. One thing that traditional foundation models are really good at or are starting to become good at, and one thing that they're not good at all. The robots need to be able to see the world and understand the context in the world. And then they need to be able to move and interact with the world. These are like two things that the robots need to do. The seeing the world part is what now suddenly you're starting to see multimodal foundation models become really good at. Everyone's familiar with all the famous sort of demonstrations in the recent world. And there's a danger of people just looking at that and saying, oh, robotics is solved, right? And that's not true, because seeing the world is only one half of the problem, and seeing and understanding the world is only half the problem. Moving through a three-dimensional world and interacting with it robustly and safely is the second half that really no sort of multimodal traditional foundation models can solve. So I think while the idea of foundation models is true, the reality is you can solve this problem by using the same architectures that foundation models are built on, like i.e. transformers and so on. But you have to do something more in terms of training these architectures to work for robots. And there are two key problems, actually. The first problem is when you actually want to build something, quote unquote, foundation model to work inside in a robotic world, the data scarcity for training is a huge problem. Like, I can't scrape the internet to train a model like this. So how do I generate the data without having 100,000 robots already in the field? This is where simulation comes in, and we can talk more about how you do it with synthetic data. That's a key problem to be solved. The second one is the model still has to work predominantly on the edge. You cannot have the robot calling back home into the cloud for every frame of data that it's seeing. So a large portion of this model I can build a 100 billion parameter model that's amazing at working in the cloud, but that's meaningless unless you can actually make this work on the edge with low latencies. So I think that foundation models are very powerful because they can allow, they can, I think for the first time, truly allow robots to function across domains. So you can imagine a robot. Previously, you would have to write a piece of code for a robot that worked inside a warehouse, and then a different piece of code for a robot that worked inside on a city street, and so on. Now I can basically have a single model that learns how to move in one domain and applies the same learning to move in another domain. That's the power of what foundation models can do. But you have to solve this data scarcity problem as well as the working on the edge problem for it to actually be practical. So I think there's a lot to be said for this being the right solution, but for it to actually be practical, these other problems need to be solved. And that's why I feel like there's maybe a little bit more hype than there's some companies who are truly working on solving these real problems, but there's some companies who are talking about it from a theoretical, hey, this is going to work great on the cloud perspective, which is not that interesting when it comes to real robotics.
We cannot have an ET phone home moment or a robot phone home. It's not going to work.
That's right.
We see the latency issues with full-blown teleoperations. We've seen them through the years. You look back at Phantom. We all know cell phones go down. Well, we triangulate it. Okay. Yes, for a short period of time it will work, but you're not going to get the 99.99% uptime. And the Verizon guy, can you hear me? I'd be like, can you drive me? It's not a scalable business, and they have to live on the edge. The robots have to be able to operate and make decisions on their own on what to do, or the business will not make sense. To enable that, you have simulation. Could these problems be solved without simulation?
I don't think these problems can be solved without simulation, because you cannot realistically collect enough real-world data. And especially, you're not just talking about the nominal case. For robots, you're talking about finding corner cases, where this famous long tail that we have talked about for years in autonomy. And there is no way you can drive enough miles to find that long tail efficiently. You can do it if you had a lot of capital, like some of the autonomous companies have done, but it's really a very inefficient way to do it. It's much more efficient if you can basically find these corner cases intelligently, procedurally, and maybe even adversarially in simulation. And I think that's the only way that ultimately you're going to build robust robotics foundation models, is using synthetic data. And then you have the inevitable challenge of figuring out how to transfer that learning to the real world. But I think that's the more tractable problem than trying to get enough real world data to train these models.
Where does this synthetic data come from? It's not going to come out of outer space. Where's the synthetic data coming from?
So the synthetic data, so it's a really good question. And I think this is where there is a very tight interaction between the architecture of the models that you're using and they're paying attention to. So people have tried to build models by trying to make hyperreal simulators. And while that can work, the problem with that is it becomes very compute heavy. So to render frames of hyperreal worlds, it's incredibly expensive and incredibly compute heavy and very time consuming. And so, even to get 100,000 frames may take you like massive amounts of compute and lots of time. So the trick, what we realized was, it turns out that about 95% of what it means to move through the world and what a robot needs to learn to move through the world is actually not specific to the domain that the robot is in. So I'll sort of use an example of my 7-year-old son learning to drive Mario Kart, the game, right? So if you have watched a kid, and I was watching my kid learn to drive Mario Kart, the Mario Kart, if you're familiar with the game, has all these different tracks where the roads look very different, the obstacles look very different, even the colors are so different and so on. But if a kid learns to drive on one of those tracks, that learning will seamlessly transfer to all the other tracks. Because what they have done is they have not over-indexed on what the road looks like or what the obstacles look like. They have developed a higher level abstract understanding of what driving means. And then they're applying it to this new track And just the part of their brain that needs to understand, oh, now my road looks orange and not blue, they have been able to kind of adapt. And so that's the way we approach this problem. And so we said, let's train the model to understand this domain independent part of moving through the world. And you can train that piece in a gaming like simulator, basically in an Unreal Engine type of gaming simulator. It does not need to look hyperreal. And once that learning is firmly established, and that learning can be established across many different domains, et cetera, it's easy to render this data. You can get millions of miles of synthetic data with small GPU clusters overnight. Then let's figure out how to transfer that learning to real world driving by showing the model, okay, here's actually what the real world actually looks like, and adapting that vision part of the problem of the model to the real world. So we have and the vision part of the problem is more solved actually, because there's a lot of vision foundation models that exist that know what the real world looks like. So we are combining this idea that you can train the movement and interaction part of the world completely in simulation. And then what the world actually looks like, it doesn't look exactly like a gaming engine, it looks slightly different. We can train the model separately on that piece. And by breaking the problem up that way, you can actually, turns out, get away and train with millions of miles of synthetic data with all these adversarially generated corner cases very efficiently. So that was the big unlock. And we think that those sorts of smart approaches are what will be needed to actually get these foundation models to train scalably.
It'll scale efficiently, but it's economically efficient, which is really smart, which raises the question, what role will gaming simulators play in the future of robotics and autonomy? Will the epic Unreal Engine be the gas behind the scene that starts to really accelerate this?
I think so, right? I mean, I really feel like, that's the approach that we are banking on, because we think that the thing about gaming simulators, and people have spent billions of dollars making these incredibly efficient in terms of how they render worlds, and also really good at being able to render things procedurally. And these two things are really important properties. The incredible efficiency at being able to render things and render physics and optics, and the ability to procedurally generate all sorts of actors and behaviors and worlds. And if you leverage those two properties of gaming engine simulators, I think you can really build very, very scalable foundation models, because now those are really what you need to train models very efficiently. Can I procedurally make all sorts of weird, challenging scenarios? And then can I just generate 100 million miles of training data very efficiently? And then just let my model basically drive in those 100 million miles for a week. I think I see that as being the future.
The future is bright. Putting this all together, we covered a lot of ground. How is Vayu going to make this a sustainable business? You have world-class investors in Khosla, world-class investors in Lockheed Martin Ventures. It's only your seed round. How are you going to make this a big business that's the most important word that my listeners care about and that I care about as an investor? Profitable business.
We are just getting started, obviously, and I think we are, in fact, in the process of raising another round and so on. But I think ultimately, we believe the answer is, traditionally, robotics businesses have been very capital-heavy businesses. And in fact, I was just having a conversation with an investor earlier today. He was saying, our venture firm has stayed away from robotics because it's we stay away from hardware and capital-intensive businesses. And I'm like, but the future of robotics is not going to be capital-intensive. And I think that that's really the key unlock, is like, if you're able to build a delivery robot for $5,000 and deploy that at scale, now the return on capital on that delivery robot can be a month and a half. Now it's no longer a capital intensive business. Anybody is going to fund a piece of hardware where I can get return on capital in a month and a half. And so I believe that's how you build profitable robotics businesses, is ultimately that if you can bring the cost of hardware down, it changes completely the economics of building a profitable business. And then ultimately, as I said, I think to you earlier, our goal is not to be a robotic operations business, right? So ultimately, I think the value is in the intelligence and the hardware reference designs that enable these things to happen with very low cost bill of materials. And that's what we will monetize. And I think that those are very profitable businesses. And also, ultimately, the value creation is because we are building things that ultimately will work across so many different applications. Sort of ability to work your same intelligence to work across many different applications creates a huge growth opportunity for you, because now you're not beholden to, oh, I can only deploy 100,000 robots in factories because there's only so many factories in the world. But the same intelligence can now work for delivering goods on the street, or it can work for mowing your lawn. And now you start seeing sort of this huge growth in the number of endpoints. So that's how we think about hopefully building a profitable business on the backs of really low cost hardware and then really robust intelligence for robots.
Multiple use cases opens up multiple revenue streams. The more revenue streams you have, the more opportunities you have. Perhaps one business grows faster than the other and you shut the other one down and you focus on that use case, but you're having a large set of data and you're really able to tell which one you're going to scale. And as the price of hardware plummets outside of GPUs, at some point that's going to get commoditized. NVIDIA investors, I'm sorry, it's going to get commoditized at some point, and then you're going to have low power solutions such as ARM. That whole chip market for the GPUs and the power is going to be disrupted. But when you have multiple lines of businesses, you have multiple ways to profit and build a successful business. Anand, as we look to wrap up this insightful conversation for today, what would you like our listeners and viewers to take away with them?
We started off talking about the fact that I think, and I truly believe, robotics is on the cusp of something very, a new era, if you will, or a golden age, because the tools in the toolbox are changing. And I think we will start seeing the ability to build very robust robotic systems across many different applications, solving real economic problems, as we have been talking about in this conversation. So I want users to be able to take that opportunity and that promise away, and listeners to take that away, while keeping in mind that you have to still separate the hype from the reality in terms of, keep in mind that you have to solve the hard problems like latency on the edge and low cost and low energy consumption and those. So companies and people and engineers who focus on solving those hard sort of technical problems while keeping in mind this incredible sort of growth potential that truly I believe exists, I think it's going to be a fun ride for people who are in that camp.
It's going to be a fun ride. Safety first, buckle up. We are on the golden age of autonomy. The dawn is here for the golden age of robotics. The future is bright. The future is autonomous. The future is value. Anand, thank you so much for coming on the road to autonomy today.
Thank you. Thank you so much for having me.